Hey, good morning, everyone. Uh, Welcome to class number 12 of our course on Network Fundamentals for Cloud. And let me just share my screen so we can get started. Okay, I hope my screen is visible and audio is fine, so we can get going. Great. Yeah, thank you, Sivachidambram. Okay, so this is lecture number 12, as we noted, and we are on the topic of data center networks. So probably today we'll complete the part of single site data center network so that from the next class we can get into the next topic, which is on multi-site data center network. So I hope today we'll be able to complete this part of our course. A quick recap, we talked about the use of NVO3 technologies to create overlay tenant-specific virtual networks on top of a underlying physical data center network. And we discussed a key NVO3 technology called VXLAN. Right? Last time we had looked at that. We understood that NVO3 is actually old wine in new bottle. It's making use of the concept of tunneling, which has for time immemorial, ever since networks have existed, been the method followed to carry packets of one protocol over an underlying network of another protocol without the underlay network realizing what it is really carrying, because it uses the concept of encapsulation. And that's what creates a tunnel over the underlay network to carry the overlay network traffic. A virtual private network is also a tunneling approach, but it also augments the tunneling functionality with encryption of the inner packet, which also secures the content of the overlay network when it passes through the underlay network. Right? So that's how tunneling has been used in the past, and it's also used in NVO3 technologies. We saw that NVO3, the tunneling function of NVO3 exists in endpoints which are called network virtualization edge nodes, which could be a function that exists in a physical switch. It could be a function that exists on a virtual switch. So NVE is a functionality that does the encapsulation in the NVO3 technology. It could exist on any form of a switch. We compared L2MP and NVO3, and we saw that both of them in reality are tunneling technologies. So they are quite similar. The difference is that L2MP uses an underlay network, which is a L2 network, whereas NVO3 uses an underlay network, which is actually a layer 3 network, something which modern data center networks also use. So that's when we came into all these VXLAN basics, and we talked about the packet format. And we saw that the encapsulation is not a layer 2 in layer 3 encapsulation, it's actually a layer 2 in L4 encapsulation or a MAC in UDP encapsulation. And we noted the reason for using UDP, the purpose being that it supports the use of ECMP more effectively. Equal cost multipath can be used more effectively when using MAC and UDP encapsulation. We looked at the use of virtual network identifier and how it can enable 16 million tenant specific overlay networks to be created on top of an underlay network. And just for completeness sake, we noted that there are three types of VXLAN overlay networks: the network overlay where VTEPs are all on physical switches, the host overlay where VTEPs are all on V switches, virtual switches, and a hybrid overlay where some VTEPs are on physical switches, other are on V switches. Typically what we find in modern data centers, right? You can have all these combinations in a modern data center. Okay, so today we will get into the topic of control plane protocols in data center networks. So when we look at so far when we looked at L2MP or Trill protocol in specific or VXLAN, we're more focused on how data gets carried. An overlay network data gets carried over an underlay network. That's what we focus on. So primarily, we've been looking more at the data plane side of the data center network. But as we noted last class, for any network to operate correctly, the data plane needs support of the control plane. We saw it in the internet where we saw the control plane runs all the routing functions which are critical for the data plane to be able to forward the traffic over the internet and for the traffic to eventually reach the right destination. Same way, within a data center network as well, control plane protocols play a significant role. In the underlay network, the control plane functions just like in the internet enable routing of traffic. And we've noted already that the modern data center network, which follows a class topology, also uses layer 3 as the predominantly commonly used protocol for the modern data centers. Okay? So when modern data centers migrate towards layer 3 IP based networking protocols, the control plane protocols that exist in the IP suite of protocols can also be used within a data center network as well for the function of routing. Okay? So if traffic, whether belonging to the underlay network or belonging to an overlay network sender, which gets encapsulated and eventually flows over a tunnel in the underlay network until it reaches the VTEP and then falls back into the overlay network, irrespective. The traffic in the underlay network is getting routed through the data center network routers using a routing protocol, which is part of the control plane. So the first part of today's class, we will focus on the control plane protocols in the underlay network, in the data center physical network, and see what kind of routing protocol choices from what we've learned in the past exist are suited for use in the modern data center. Once we've understood that, we will get to the second problem, which is a problem related to the tunneling of traffic in the overlay network. So the point that we noted, the question that we asked last class, and I said, keep in mind, this is something we'll answer in the next classes. How does the source VTEP serving a source sender node, a virtual machine maybe, knows the destination VTEP serving a destination VM? So if the traffic has to be encapsulated and then routed over the underlay network, the destination VTEP has to be known. And that is the only way the underlay network will be able to take the traffic from the source VTEP and route it towards the destination VTEP. Afterwards, the destination VTEP will do the function of decapsulation and forward it to the destination VM. But how does the source VTEP know which is the destination VTEP serving a destination VM? That was the question we had in mind. That is where we will look at the control plane protocols of the overlay network, specifically the VXLAN protocol, and what are the control plane protocols in the VXLAN protocol, which help solve this problem or which help exchange this information between VTEPs as to what all VMs are they supporting or handling. Right? So these are two parts that we will cover today. So let's start now by emphasizing and kind of summarizing on the way a data center network's underlay physical network looks like. So far we said, okay, it's a simple leaf spine topology, which is a variant of the class topology. But the leaf switches in a leaf spine topology can also be of different types in a data center network. Now, I will like to take your attention back to the case study from last class, where we looked at the multi-tier hierarchical leaf spine structure followed in the Facebook data center network. So in that architecture, we saw a three-tiered topology of leaf spine switches. I mean, the building block being a leaf spine topology. But we saw the existence of special type of leaf switches called the edge, or special pods called the edge pods. And we noted that these edge ports are necessary because they provide connectivity to the external networks. Those external networks could be another data center network, or it could be the internet itself. So we noted this edge pods being segregated and separately marked from the rest of the fabric pods, noting that they have some different functions to perform in a data center. Okay? And when we were discussing the network function virtualization and SDN and the role that these two technologies play in a data center network, we noted that client traffic or tenant traffic often needs to pass through multiple different network appliances, something which we had called as service chaining. SDN helps us create that service chain, but the appliances in that service chain are most of the time virtual network functions. Right? And that's where NFV comes into picture. So we had looked at virtual network functions like a virtual firewall, a virtual antivirus device, a virtual video optimizer. I'm using the word virtual explicitly because just to denote that they're all implemented in software. They're not physical hardware driven appliances, but they're more software driven functions, network functions, which run on common off the shelf server machines available in a data center. These devices, which actually perform certain special functions, network driven functions on the traffic, are also sometimes called value added service devices or VAS devices. Right? They're providing some additional value, like an antivirus would screen your traffic for any vulnerabilities or any malicious traffic coming in, malicious URL. So it's actually a value added service, right? It's not a server like the rest of the servers are in the data center network. It's a special server. It provides some value added service, a load balancer, application load balancer, network load balancer. These are all special value added service devices. So when you look at a data center network underlay, physical network, a DCN underlay network, yes, you will observe the leaf spine topology. So we still see that there is a fabric structure where you have these spine switches, which are connecting leaf switches. The leaf switches that we've been talking of so far are actually are sometimes differentiated from the other leaf switches and called server leaves. The term server leaf denoting that these are the top of rack switches that exist in a rack of servers and is a leaf switch that enables connection to the physical server machines in the rack as well as the virtual machines that run within these physical servers. Okay, so it's called the top of rack switch that we've been talking of so far, or we've called it the leaf switch, is also sometimes characterized as being the server leaf, noting that it connects to physical servers and virtual machines within those physical servers. Right? So that's where the server leaf comes in. But because we also need external network connectivity to other data center networks or to the internet, we need such kind of edge pods. And these edge leaf switches are also called border leaves. Okay? Just like in the internet, we used to call these border gateways routers, and we used to distinguish them from the routers that were used within the autonomous system. We said inside the autonomous system, you have routers, but then the routers which sit on the edge and connect to other autonomous systems, they are special. They are called the border gateway routers. So the border leaf switches are special purpose switches which are actually connecting to the routers in the provider's network. The provider network could be your ISP network, right? Provider edge network or any other network that enables access network that enables connectivity to the external network. So these are border leaf, right? That's what you note over here in the table. So these are the ones that are receiving and transmitting traffic to from external network. And when the traffic comes, let's say from the internet, let me erase what I've drawn so far. Let's say some traffic originates from the internet, reaches an edge pod or a border leaf in the terminology that we have now, it will forward it towards the spine. But if we are using that NFV service chaining that we saw earlier when we discussed SDN and NFV, I want to create an NFV service chain. So SDN will configure my flow tables in all of these switches in such a manner that that service chain can be created. That is what we had seen earlier. So essentially, SDN will set up the flow tables in these border leaf switches as well as the spine switches, so that the traffic coming from the external internet over here gets routed first towards the service leaf switches, which can pass it to the VAS device. Once they pass through the VAS device, maybe I need another VAS device. So after passing it through the antivirus, I want it to go through a firewall. So I pass it to another VAS device, comes back, and then I route it towards the right server. So this pathway, which we also earlier called as the traffic service chain getting created, where I say, okay, before this traffic meant to a server can actually reach that server, it needs to go through a few value added service functions, which could be load balancing functions or antivirus, video optimizers, firewalls, and therefore the SDN flow tables might be configured in such a fashion that they first go through the VAS devices before the traffic eventually gets routed to the server. And therefore, when you learned that Facebook data center network uses a distributed routing protocol within the fabric, but there is a method of centrally overriding that. It really meant that, okay, once the traffic reaches the spine and has to go to the server, it can follow the distributed routing protocols in the fabric network to get routed. But this override that I have to do, where I actually want SDN to help me create an override path so that the traffic just doesn't go directly to the server, but first passes through certain value add services, I can use a central override using SDN to enable that kind of a thing. Okay, so we would like to distinguish sometimes between the different leaf switches that exist within a data center network by saying, okay, some of them, most of them are actually server leaves. They're top of rack servers catering to the servers in that rack. But some of them have a special functionality in the sense that they're border leaves, they're helping us connect to the external networks. And still some others are actually service leaves because they connect to servers, of course, just like server leaves, but they connect to some special purpose servers. Once those that provide value added services like firewalls, load balancers, and so on. Okay, so that is what a DCN underlay network looks like. Now, our problem is, okay, we will not get into the central override part, which I had drawn earlier, because we know this is something that can be easily achieved using SDN, and that we've learned that by intelligently setting the flow table in the SDN class. I had also taken one example where I said, okay, how can you enable this traffic steering? What will you do? If you want traffic to flow via a particular path, what will you do? You will set the flow table in this node, over here, in this device. You will set the flow tables accordingly. That's what SDN is capable of doing. So with that part, we know. But once now the traffic reaches back into the fabric, to the spine, and it needs to go now to a particular server, how does this traffic take a path through the fabric to reach the server? That's the control plane that we are going to talk about. Okay? So, because the data center network fabric itself is a layer 3 protocol, which is IP protocol, the routing protocols that are used in the data center network underlay part are also the IP suite of routing protocols. Okay, so Jyoti has already mentioned on the chat window protocols like ISIS, which we saw was something that Google was using in their Jupyter data center network topology, the case study noted that protocols like OSPF, even protocols like BGP can be used in the underlay network of the data center. Okay, just like they're used in the internet. Of course, in the data center network, unlike the internet, it is strongly recommended that in order for the network bandwidth to be optimally utilized, we know in the spine there are multiple paths to reach the same server. Right? You can draw so many different paths to reach the same server. Because there are multiple paths to reach a server, you can optimally utilize the network bandwidth by using a multi-path protocol like ECMP. Okay? So ECMP is highly recommended to be used in addition to a dynamic routing protocol like ISIS, OSPF, BGP in order for traffic from one leaf node to one server get distributed across multiple equal cost parallel paths in the network, which enables the traffic to get higher bandwidth or higher throughput. And it also guarantees better reliability, because if one of the paths was to go down, there are still alternate paths that are being used. So ECMP is highly recommended in modern data center networks. Let me take a pause, look at the slightly elongated long question that Ravi has on the window. Let me read that and we'll go. Sir, can we achieve this class design at virtual level as well? From design perspective only, not the protocol level, as hyperscalers are responsible for the design of protocols. Example, I need to design a network in the cloud for an enterprise. Can I leverage class design there? In current case, we use generally hub spoke network topology or mesh for SD-WAN. That is correct, Ravi. So you are right. Most of the time when I create a virtual network or an overlay network, a tenant specific overlay network, there is a reason why we use the hub spoke network topology. So to answer your question, I can create a class topology in the virtual network as well. Okay. Whether I will benefit out of creating a class topology is questionable. And the reason I say that is because the virtual network is actually virtual at best. What I mean by that is the traffic doesn't flow in the virtual network. It appears as if it is flowing in the virtual network. But in reality, the traffic between two nodes or two VMs in the virtual network also flows over the underlay network. It gets tunneled over the underlay network. So the benefit that I am trying to get of multipath is really existing not in the virtual layer, but in the underlay network. And that is where, because we are using class topology and because we are using ECMP and you actually asked the question at the very right time, because the recommendation of using ECMP is for it to benefit not the traffic flowing in the underlay network, but really to benefit the traffic of the overlay network when carried or tunneled in the underlay network. Okay, so whether I configure the overlay network using a class topology, I can do that. Nobody stops me from doing it. But whether it will give me any additional benefit is difficult to say, because the benefit comes from the underlay network using multiple paths to really carry that traffic. In the overlay network, it will just appear as if it's going from one VM to the other VM, whereas it's really getting carried in the underlay network where the performance optimization by using class topologies and ECMP can be achieved. Something else I wanted to note as well, which, yeah, okay. The last part to your question, the last part of my answer to your question is, why do we then use so often a mesh topology or a hub spoke network topology? Is because of the additional benefits that come out of these topologies over and above the benefit of using a class topology in the underlay network. This part as to what is the benefit of using hubs and spoke topology is something that probably in the 15th class, when I start talking about network performance, observability, security, I will touch upon why hub and spoke network topology is so popular in the virtual overlay network of a data center. Okay. So that's the answer that I have to your question, Ravi, at this time. Jyoti has put in something in cloud or virtualized environment. The cloud architecture represents multi-tier fabric that provides higher bandwidth, low latency, scalability. Correct. Right? And that's where the underlay network provides its value. Okay, so yeah, I think the question that Ravi asked only re-emphasized why ECMP is recommended because it benefits all the tenant networks that are going to be configured as overlay networks on top of this DC and underlay network. And by using ECMP, all my virtual overlay network will reap the benefit of implementing load balancing and backup, redundancy, reliability, while also ensuring that the entire network is getting equally loaded and the entire cross-sectional network bandwidth. I had said earlier also, we denote this as the so this as the cross-sectional network bandwidth. All these links put together are my cross-sectional network bandwidth. I can optimally utilize this entire bandwidth that I have by using ECM. Okay. So if I can use ISIS, OSPF, BGP, just like I do in the internet, we also, when we discussed the internet control plane, we noted that in the internet, OSPF and BGP are not treated at the same level. BGP is the link state routing protocol. So is ISIS. ISIS and OSPF are both link state routing protocols, whereas BGP is the path vector routing protocol. And we saw that both have their own ways of exchanging information with peers, which one to use where largely depends upon the size of the network. So we said OSPF cannot scale to large size network. So only within an autonomous system, and therefore we said it's an intra-autonomous system routing protocol. Whereas BGP can scale very well. It reduces, BGP scales by aggregating information into paths. It doesn't exchange very fine granularity information, but that is what also helps it to scale. And therefore, we saw that in the internet, it's actually used as the inter-autonomous system protocol, primarily the eBGP part of it. While we also noted that it has an inter-autonomous system part as well, which is iBGP. So, but it's a different protocol normally used for larger sized network. Now, if I look at a data center network, because of the fact that it belongs to a single vendor, I can see it as an autonomous system. And therefore, for all practical purposes, I should be able to use all intra-autonomous system protocols like RIP, OSPF, ISIS, all of them are possible to be used within this. Right? But not all have become popular in reality. Okay, Jyoti has a related question why EIGRP is not recommended in the data center network. There is no reason, Jyoti. Right? There is no reason why I would be able to say that EIGRP is not something that you should use. It's just that some protocols have been known to work better, whereas you can take an EIGRP protocol as well, tailor it for your data center network and it will also work. Right? As we saw in the Google case study, Google uses ISIS, whereas most data center networks otherwise, which are set up in enterprises and otherwise, they don't use ISIS, they rather use OSPF. Maybe because OSPF is highly popular in the internet, and because its popularity lends to better reliability and adaptability. It evolves faster. There's a community of people working towards improving the protocol. And that is why it's a preferred choice for a lot of people, right? So in reality, there is no recommendation that IETF or any standardization body puts forward as to what is the routing protocol that you should use. And to be fair to all protocols, I think any of the layer 3 routing protocols that are defined by the IETF standardization body, they can be used in a data center. But the preference towards certain protocols like OSPF or BGP is because of their popularity. They are more commonly used in the internet. And when they are used in the data center network, one of the benefits that people seem to see from these protocols is the better interwork. I mean, they're proven to be interoperable. When you use within an inter-autonomous system, OSPF and BGP in the internet, we know that these interoperate well. They work well in the internet. Okay? Yes, Jyoti, that's also a point. EIGRP is not an open standard. It's a proprietary protocol. That is another reason why, as I said, when a community backs a protocol, it becomes more popular than something which is not open source, not community backed. Okay? So that could be a reason. But to be fair, I think EIGRP can be used also in a data center. Okay. So which ones should I use when? Okay? When should I use OSPF or when should I use BGP? Because while there is no recommendation, the preferred protocols that are often used in modern data center networks are either OSPF or BGP. In the case study that we saw for Google, we saw ISIS also is being used. But then ISIS is always been more like EIGRP, a more of a proprietary protocol. It's evolved from being a proprietary protocol to being standardized. And therefore, OSPF being born as an open source protocol has always seen much more backing and support than a protocol like ISIS. Okay? But ISIS, OSPF are quite similar. I mean, they're not way different. So which protocol should I select? How should I decide whether my data center network should run OSPF or should it run, let's say, eBGP? Right? The choice is largely driven, as we saw in the internet as well, on the size of it. So yes, the data center network is an autonomous system, but unlike other autonomous systems which are normally smaller in scale, a data center network can have a very huge scale. Okay? It can be from a few tens of nodes to thousands and tens of thousands of servers. Okay, so how do I decide which protocol to use? Based on size. The general recommendation, and this is where the recommendation part comes in. The recommendation is to use OSPF, and it's something which is preferred when your data center network is actually a small data center network or even a medium-sized data center network. A rule of thumb, actually, there are two rules of thumb that are followed. One rule of thumb is you can look at the number of leaf nodes that exist in your data center. If the number of leaf nodes in your data center are less than 100, you can use OSPF. It will work well, right? You get the granularity of information exchange that OSPF brings in with its link state advertisement. And the convergence also happens fast enough in a network that is not more than 100 switches, 100 leaf nodes. Right? But if the number of leaf nodes goes beyond that, an order of magnitude more than 100, then it's preferable to use BGP because we saw that when the network size evolves, OSPF will take longer to converge. The information exchange that happens in OSPF because of the broadcast of link state advertisements will become a very big overhead. It will be control plane overhead in the data center network will become a significant percentage of the entire bandwidth. And because that is often considered as a wasted resource or a necessary evil, it's not something which is really carrying the real data. So eBGP in a network which is larger scale is still a preferred underlay protocol. Okay. The other rule of thumb, which is also sometimes followed, instead of counting on the number of leaf nodes, the other rule of thumb is to count on the number of network prefixes that needs to be advertised. So in a routing protocol, as we saw, what am I advertising? I am advertising reachability to a node, and that node could either be a particular IP address like A.B.C.D, or an aggregate subnet like A dot B dot star dot star. So this is something which we call as a prefix, because A and B are prefixes and the rest are any or star. So how many prefixes do I need to advertise? So when the number of prefixes that are needed to be advertised are actually fewer than 32,000, OSPF is a fine choice to use. But if the number of prefixes grow, which is another way of saying that it's a huge network, there are multiple smaller subnets within that large network, and that is why there are so many prefixes. And it kind of become at the coming to the scale of an internet itself, it becoming so big. So whenever there are more than 32,000 prefixes, BGP once again becomes the go-to routing protocol. Okay? So there is no hard definition of when to use BGP, when to use OSPF. Larger data center network operators like Facebook, Google, they found their own sweet spot over decades of optimizing their data center network operations and the control planes. They've landed into a hybrid model for the control plane, which is what they said to be the distributed routing with centralized control. So they have their own sweet spot that they've identified over years of tuning, and they find this is what works best. Okay? There is no hard and fast rule on what you should use and where you should use, but these are just some recommended rule of thumb principles that you can use when in doubt. Okay, this is a, I mean, it's kind of more is a number that helps you scale your network, size your network rather than, right? Size the scale of your, let me keep it simple, size your network. If less than 100, it's a small to medium size, use OSPF. Less than 32,000 prefixes, it's a small to medium network, use OSPF. More than 100 nodes or more than 32,000 prefixes, it's become a more complex, large size network, prefer to use BGP. Okay, so OSPF can very well be used and deployed in a small to medium data center network. You can use it in the normal sense that we discussed OSPF to be, with just one area configured. So all leaf switches and all spine switches, including the border leaves, you can treat all of them as one OSPF area and use OSPF within that thing. So we are saying that the entire network is actually a single fabric network because it's not a very large network, maybe a less than 100 leaf nodes. So I've designed it as a single fabric network. I can uh, generally run OSPF like we learned OSPF works. But if even when the size of the network is slightly larger, or when I'm using like Facebook does, a multi-tier hierarchical structure of my data center network where I have multiple fabrics and then a super spine plane connecting all these fabrics together, I can actually use hierarchical OSPF. So while we had not discussed hierarchical OSPF in a lot of detail earlier, I had noted that hierarchical OSPF is a method where you can create areas. OSPF protocol allows you to define areas. Areas are not same as autonomous system. Areas are within the same autonomous system. It's still intra-autonomous system. I can define areas. OSPF, an instance of OSPF runs in each of the area. The border area routers aggregate information and exchange with each other over a next level area called area 0. Okay, so you can think of it like the backbone area where these are individual fabric areas. So when you have a larger multi-fabric architecture like Facebook had, you can still use OSPF with one instance of OSPF running in each fabric configured as an OSPF area, and aggregated routes between areas being exchanged over the superspine plane, which itself can be configured as area 0, OSPF area 0. Right? Now, it's also possible, right, to see the fabrics. I mean, there are various ways you can configure this, right? This is one deployment. Now, it's also possible to see the multi-fabric network like we see in the picture on the right hand side. As okay, so in the what are we seeing on the right hand side? We are saying that this is one single VXLAN domain, means a single instance of the VXLAN protocol runs across both the fabrics, across the entire fabrics and the super spine. I can even configure a data center network to have fabric specific VXLAN domain. So different instances of VXLAN protocol also running across fabric. It's like having two data center networks physically co-located. Okay. But I mean, this is more of a multi-site data center network topic, which I'll start next class. In reality, when we talk about multi-site data center networks, we are typically talking of data centers that are geographically segregated in two different geographical locations. But nobody says that that is the only way you can have a multi-site data center network. It's also possible that I say, okay, each of these fabrics within my physical data center, I can configure them as separate VXLAN domains as if they were two separate data center networks, but physically co-located. And just like multi-site data center networks also need to be connected together, which we will talk more next class. It is also possible that each of the fabrics I run just OSPF individually, and then the interconnectivity between fabrics, rather than using it as OSPF area 0, I can use BGP. Because this is like connecting two different autonomous systems, AS1 and AS2 together. Okay, so depending upon how you are treating your fabrics, are they part of the same data center, which means they are same single VXLAN domain, or are they to be treated as two data center networks physically co-located in the same geographical warehouse location? Right? You can flexibly choose your control plane protocols, but we don't have a need to come up with a new set of control plane protocols. The existing ones that are used in the internet, they can very well work in a data center network as well. Right? As I said, the sweet spot that many data center network when operators have figured out is to use a combination of these distributed routing protocols with SDN as a method for central override. Okay. Google, on the other hand, did say that they use a complete centrally controlled SDN driven control plane. Okay. But Facebook uses more of a hybrid approach. So essentially, we are saying the data center network underlay part, the control plane is either pure SDN or pure OSPF, BGP, distributed routing protocols, or a combination. It can be a combination, right? With distributed protocols doing the bulk of the work, SDN playing the role of a central override, right, on these distributed protocols. Yeah. Okay. So just like OSPF, we can also use eBGP as the protocol. So in this diagram, I have arbitrarily segregated it's a single fabric. But what have I done? Of the 6 leaf switches that I had, I bundled 2 each randomly and called them an autonomous system. And then the spines, I called them another autonomous system. And I said, okay, this is how the autonomous systems are in my data center network. Now I can use eBGP between them. Okay. So a group of leaf nodes have been added to an autonomous system. Spine nodes have been added to an autonomous system. I have kind of set up those eBGP sessions, peer-to-peer relationships between the switches in these autonomous systems to use eBGP for information exchange. So what do they exchange? They exchange more path information. So they are exchanging prefixes, but aggregated prefixes and only exchanging path information. Okay, this I have reachability to this prefix, it goes via this autonomous system. The path information, it's a large size network, it's easy to use BGP because it will, as we know, scale way better. Right? Same thing I can do like I did with OSPF, I can do with multi-fabric networks as well. I have multiple fabrics. Each fabric I can configure like we did on the previous slide as a single fabric. So each fabric individually is configured the way we did saw on the previous slide. Okay? We have autonomous systems. And then the super spines can be part of another autonomous system, and I can create a next level hierarchy between the spines and the super spines exchanging information. So it's what? It's like a multi-tiered internet architecture where we know BGP anyway works well, eBGP works well. So these guys are exchanging path amongst themselves. This is furthering that information forward. So if there's a prefix over here, which is being advertised, when this guy advertises it to the next, it will say it's a two path reachability to that prefix. It goes via AS 63500 and then 63501. It's path vector protocol. That's how it's getting advertised. I'm sure you understand this part because this is exactly how BGP works in the internet also. So essentially, the deployment models for BGP and OSPF are similar to what we see in the internet. I can look at my data center network in a variety of ways. Each fabric as a separate thing, or if it's a single fabric network, only not a two-tier architecture only, not a three-tier hierarchical structure. I can put all of them into a single domain. So I can have different methods of deploying the control plane protocols in my data center network. So that's the underlay part of it. Now let's come to the second part, the overlay network, where we want to talk about the VXLAN control protocol. Basically, the question, how does a source VTEP know which destination VTEP it should tunnel the traffic to over the underlay network so that the traffic can reach the destination VM? So if you remember, this is the diagram that we had. Or I have the diagram. I think in the recap part I had it, right? Yeah, this is the diagram. So this is the source node in the overlay network. It is a VM. Let's treat it as a VM. It's sending traffic to a destination VM. So the traffic goes to the source VTEP. Here in the underlay network, the traffic will be routed using what? The outer IP packet. Yeah, the information in the outer IP packet. Again, if I go one more slide back, where was the format? Yeah, this was the packet format, right? So I don't care about this inner. Okay, extended it. Yeah, I don't care about what is the information carried in this inner overlay original L2 frame, because this is what? This is the overlay network traffic from one VM to the other. What I've done at the VTEP is this encapsulation. Within the underlay network, the routing of the packet in the underlay network that we just studied happens using BGP, OSPF, will happen by looking at the outer IP header. So what should be the outer source and destination IP addresses? We had talked about it last time. This is the IP address of the destination VTEP. And this is the IP address of the source VTEP. So in the diagram earlier, this is the source VTEP, this is the destination VTEP. These are the addresses which will go in the outer IP header of your encapsulated packet. So naturally, the traffic will get routed from source VTEP to destination VTEP. And because nobody looks at the inner packet, it's like seeing it like a tunnel being created between the source VTEP and the destination VTEP. That's a tunnel. So all this traffic which is coming gets encapsulated, tunneled to the destination, and then delivered to the destination. So the same question which Ravi had asked a while back, the benefit of class topology that I'm getting is actually here. Overlay network, it just seems as if the traffic initiated from the source VM and got somehow delivered to the destination VM. It appears to have been routed or switched or forwarded in the overlay network. The question still remains what we asked last time. How does the source VTEP know what is the destination VTEP to set up the tunnel with? Or in other words, in this slide, when the source VTEP is doing this encapsulation, how does it know what address to fill in this field for a given VM, or destination VM? How does that get to know? So that is where the control plane of VXLAN comes into picture. So in very simple layman terms, VXLAN control plane is a method for VTEPs to exchange amongst themselves information about which destination nodes, and these nodes in a cloud computing environment are actually going to be VMs or some VNFs, virtual network functions. They are virtualized machines or virtualized network functions. Which ones are serviced by what VTEP? This information is exchanged amongst the VTEPs using the VXLAN control plane. Okay, is that so far so clear? We'll look at how, but remember that this is the information that is getting exchanged between the VXLAN control plane is between the VTEPs and is a method for exchanging information about which VTEP connects to or services which destination nodes, which could be VMs, VNFs. Okay. So the reason why we still call it a control plane and we treat it like we treat a control plane in the internet or in the underlay network is because what were we doing in the underlay network or in the internet? There, routers were exchanging information of reachability. Every router was telling the other routers or its peers what nodes or prefixes, node prefixes, are reachable via it. So control plane protocol, even in the general sense in the internet, layer 3 control plane protocol was exchanging reachability information. In the VXLAN control plane, for the overlay network to work, we are doing the same thing. We are exchanging reachability information of destination nodes via a VTEP. Okay. So there are two widely adopted methods that are possible to use with VXLAN for exchange of this information. One is like we do in a layer 2 network, right? So remember we said layer 3 networks have routing based control planes. Layer 2 networks don't have routing protocols. They are self-learning network. They use what is called as a flood and learn methodology. So when you have a network of layer 2 switches, L2 switches, we call it a L2 network, a L2 forwarded or L2 switched network. The forwarding information is learned. Right? This is something we talked earlier as well. These switches are called self-learning switches, and the network is a self-learning zero configuration network, because when I don't know how to reach a destination, I broadcast. But gradually I learn which node is connected to which switch, and I keep populating my forwarding tables. And without having an explicit routing protocol, I can perform self-learning in a L2 network. So that's one method of exchanging or learning about reachability. The other method of learning about reachability is to have an explicit routing protocol. Now, which method is better? Strictly, as we saw earlier, depends upon the size of the networks once again. So if I have a smaller size network, a local area network, I can use self-learning properties of layer 2 switches to set up the forwarding tables. But as soon as I get to the scale of the internet or a wider area network, the broadcast flood and learn methodology does not scale. So I use the routing based methods, protocols. Okay. VXLAN also provides you both choices, which you can decide to use primarily based on the size of your network, data center network. Okay. So one technique is a flood and learn method. It's called multicast based because the flooding is not a broadcast but a multicast approach. Why? I will just answer in a while. But the underlying fundamental is still flood and learn. There's no routing protocol. The learning of which VTEP services which end nodes is dynamic self-learning approach. And I learn that via the flood and learn principle. Okay. In general, when we say flood and learn, we actually are flood means broadcast. In VXLAN, flood, however, means multicast. Why? I'm just going to come to it in the next slide. So that's one method. And typically, as you can make out, used in small to medium sized networks. It will not scale to larger size data center networks. So for the larger size data center network, the VXLAN control plane is also based on kind routing like methodology where routing protocols are used to exchange reachability information. And this is where multi-protocol BGP, it's an extension to the basic BGP protocol called MP-BGP, multi-protocol BGP. EVPN stands for Ethernet VPN. An MP-BGP EVPN control plane protocol is useful in large size networks. Okay, so both options exist. Which one to use once again depends on the size of the network. Neither is the flood and learn approach new. It's something which has existed in networks for a very long time. Nor is MPBGP a new protocol designed for cloud environments. No. I'll talk about what is MPBGP. It's existed for decades. Okay? It has been in existence even before cloud computing got used. I'll tell you where it has been used in the past, how it has been used, and how it can be used in cloud environments with VXLAN. Okay? But these are two options that exist in the VXLAN control plane. So let's one by one talk about both these options and understand how this information of which VTEP services, which endpoint nodes gets exchanged for the overlay network traffic to be forwarded. Okay. So what is the time? It's 11:28. Okay, yeah, almost 1 hour boundary. So what we will do is write logical point to take a 5 minute break. And once we come back, we will one by one look at both these control planes. So, okay, it's 11:29 now. So 11:34 by my watch, I will start. Come back in 5 minutes. Okay, guys, 11:34. Let's start. We had a break. What happened? Yeah, this is where we are. Okay. So VXLAN, the first option in VXLAN control plane is called the flood and learn multicast based control plane. So as I said, I just explained before the break, the underlying principle is to flood and learn, which means that if I don't know which endpoint is serviced by what VTEP, rather than ignoring or dropping that traffic, I instead flood it to all. Okay? But when I flood, I am also sharing certain information, because in the flooded message, while the message carries in the inner packet the destination VM's address, and in the outer packet the destination VTEP's address, which when I don't know, I will flood it. Right? The inside carries the source VM, which is sending it, and the source VTEP. So when I flood a packet, in general, I am disclosing information that the source VTEP services source VM. So gradually, the learning tables start to build up. Right? Gradually, the hosts in the network, based on this flooded traffic, start to learn MAC to VTEP mappings for the VXLAN segment and start populating. Eventually, the forwarding table will become up to date and no new, and this control plane would have solved its purpose. Now, in general layer 2 networks, the flooding part is done using broadcast methods. Okay? So I broadcast in a layer 2 network a layer 2 frame when I don't know who is the right recipient for it. When I don't have the MAC address, I'll just broadcast it over the L2 network, right? So I don't know what is the MAC address of a destination IP. Let's broadcast it. Okay, so we can do the same thing here, but the fact is the underlay network that we are operating on is a layer 3 network. The underlay network is not a L2 network. So when I flood, I don't broadcast. Instead, I use what is called IP multicast. So IP multicast is also an existing method used in the internet. It's a protocol which is very well defined by the IETF. There's a protocol called the IGMP, Internet Group Management Protocol. IGMP is a protocol that routers in the internet use to advertise and join multicast groups. So what is a multicast group? A multicast group is a group of nodes which form a group saying we all want to be part of this group. It's like a broadcast group, but limited to a set of people who've joined that group. It doesn't go to everybody, but to only a select few people. So it's not unicast. It's not unicast because it's not going to one person. It's multicast. So when I send one of these people sends a frame or data packet, it goes to all members in the group. This is called multicast. It's an existing approach used in the internet and uses the IGMP protocol. That's a standard protocol defined by the IETF. In the cloud environment, the way this is used is every VNID or tenant network that exists is mapped to a IP multicast group. Okay, so if I have 10 different VNIDs, it's like saying I have 10 IP multicast groups that exist. So whichever VTEP, So every VTEP knows what is the VMs that it is serving to. Right? Every VTEP knows which all VMs are connected to it. It also knows what is the VXLAN segment or VNID, the virtual network that these VMs belong to. If I once again go back to that diagram, I think that may be easy to explain this part again. Yeah, this diagram. So let's say there are two VTEPs over here. This VTEP knows I am connected to three VMs. One VM belongs to VNI 5000, the other belongs to VNI 6000, the third belongs to VNI 7000. What we've said is for every VNID, there's an IP multicast group that is configured. Okay? So for every VNID, there's an IP multicast group. Now, as a VTEP, if I am connected to three VMs of VNID 5000, 6000, and 7000, what I do is I use the IGMP protocol, Internet Group Management Protocol, to join these three multicast group. I'll join the multicast group for VNI 5000. I'll also join the multicast group for VNI 6000. And I will also join the multicast group for VNI 7000. So I'll not join all multicast groups, but as a VTEP, I will join all those groups. It's like joining WhatsApp channels. I mean, since in our generation now we are more familiar with WhatsApp groups. Think of a WhatsApp group like a multicast group. That's what a WhatsApp group is. It's a multicast group. There's a control plane. You join a WhatsApp group by choice. So VTEP joins an IP multicast group depending upon what all VMs it is serving and which VNIs those VMs belong to. All VTEPs do the same. Depending upon their the VMs that they are supporting, they all connect to the relevant multicast groups. Once that is done, now when I have to flood, okay, so when there is a source VTEP which has traffic for a destination VM, and this destination VM belongs to VNID 5000, the source VTEP just has to flood this traffic on the IP multicast group for VNID 5000. Okay. Ravi, how this joining works, I will not be going into that because that will require me to get into one more protocol, which is the IGMP protocol. Okay. I'll just limit by saying there is a well-defined standard IGMP protocol that exists followed in the internet, which allows nodes to advertise that they are joining this network. Okay, so these get configured in the network nodes that so many nodes are member of the IGMP, and when a traffic comes for an IG, so there are special IP addresses which are called multicast IP addresses. And when a packet comes for a multicast IP address, then the packet is forwarded to all those nodes which have joined this multicast group. Yeah, so PIM is the protocol that is used as Jyoti mentioned. Protocol independent multicast is used to forward the traffic. We'll not get into that because that's a whole new protocol that we'll just get into. So it's existing internet-based protocol that is used. We are just reusing it in the cloud environment. Okay, so I'll take an example to help you demonstrate step by step how the VXLAN flood and learn multicast-based control plane work. I've created in this diagram a simple network. Right? There's the underlay network, which is the IP network, layer 3 network. There are three VTEPs, VTEP 1, 2, and 3. Each VTEP is servicing two endpoints each. Okay, while they are drawn as physical servers, they can be a physical server or a VM. As we learned in the last class, VXLAN doesn't differentiate. It is an endpoint. So there are three VTEPs. There are each VTEP connected to two endpoints each, and there are three VTEPs connected via an underlay network, which is an IP network. Okay. Now, end system A, okay, wants to talk to end system B, where end system A and end system B are part of a virtual overlay network that is created over the underlay IP network. Okay. So what is end system A going to do? End system A will see normally what happens before I get to that diagram. If it's not an overlay network, if it's a L2 network, a general L2 network, okay, and there is an end system A and an end system B, and on this network, I want to send some IP packet from A to B. So what happens is the destination IP address will be B. When A has to forward that to B, it will look up the forwarding table to see what is the destination MAC address corresponding to the destination IP address B. Since it doesn't have that, it will broadcast the traffic. Okay. Now, what is the traffic that gets broadcast? The broadcast traffic is actually an ARP request. So the node sends out an address resolution request. It's a broadcast message that goes to everyone saying, I have a packet that needs to be delivered to IP address B. Whichever node has this IP address, send me your MAC address. Okay. So this message will, ARP request gets broadcast. Address, it's called an address resolution protocol message. It gets broadcast with a query. It's like a query saying, I have a packet that needs to be sent to destination B, IP address B. Give me the MAC address because it's a L2 network. I need the MAC address to switch that traffic. The packet, the ARP request gets broadcasted to everybody in the network. B also receives it, sees that the IP address matches its own, sends back a unicast ARP reply, ARP response back to the destination saying, I own this IP address and this is my MAC address. Once A has gotten the MAC address, it will be able to unicast an L2 frame to the destination. Now, in this whole flood and learn, where is the learn part? So when I broadcast an ARP request, the ARP request is also carrying my source IP and my source MAC address. And this broadcast message is going to all. So the ARP request helps other nodes in the network create a mapping between the source MAC address and the source IP address. And this is where the learning part comes in. Okay. Same way, the VxLearn flood and learn multicast based control plane protocol also runs. So in this end system A, which is part of a layer 2 network, overlay network, wants to send a packet to end system B. End system A has an IP address IPA, a layer 2 MAC address MAC-A. End system B has an IP address IPB, MAC address MAC-B. So when there's an IP packet that end system A has with destination IP address B, source IP address A, but it doesn't know the end system which will handle IPB, it generates an ARP request. So end system is just behaving as if it would do in a normal network. It doesn't care it's an overlay network. It normally generates the ARP request. Okay, the ARP request is generated in order to discover the MAC address of end system B, which is MAC-B. Okay? Now, what will happen? This ARP request will reach VTEP1. VTEP1 will see, okay, this is a MAC address, sorry, an ARP request with destination IP address B. Do I know which VTEP service is it? And do I know where to forward it? Let's assume that initially the system has just started up, so all forward table entries, nothing has been learned, it's empty. So VTEP1 doesn't know where to send this ARP request. What will it do? It will flood it. Okay? It will flood it over the multicast group for that VNID. So this multicast, so ARP request is the request which is being sent or is being flooded, but not broadcast. It's being multicast over the specific multicast group created for that VNI. End system A and end system B are part of a VNI. So in a way, I'm broadcasting this ARP request. I should not use the word broadcasting. I am flooding this ARP request, but the method of flooding is multicast. So it only reaches those VTEPs which could be interested parties, which are the VTEPs which are catering to end systems belonging to that VNI. All other VTEPs which are there in the network but do not cater to any end system in that VNI, there is no point in forwarding the traffic to them. So multicast helps a more optimized, efficient flooding to only those VTEPs which are involved with the VNI in question over here. Now, what happens? All VNIs receive this multicast request. So what will they do? The learning function will also come into existence. They will learn as part of this ARP request that there exists an end system A, and that end system A is reachable via VTEP1. How did they learn this? Because it was VTEP1 which put that multicast ARP request on the multicast group. So every other VTEP, VTEP2, VTEP3, they learned that end system A is actually reachable via VTEP1. This is something they've learned. So as part of the flooding, the learning is also happening simultaneously, just like it happens in the normal L2 network. Now, VTEP2 and VTEP3 both receive the ARP request. So the multicast packet reaches every VTEP that has joined that multicast group. That's step 3. So each VTEP receives it, de-encapsulates the VXLAN packet, learns that the system A MAC address exists, and this is connected to VTEP1, and that's where this learning table entry comes in. Now, as step 5, after they've learned, they also have to forward the ARP request. So each VTEP will forward that ARP request over its local connected network connections, right? It will forward that to its local destination. VTEP3 is connected to an end system C and some other end system. These end systems will just ignore this ARP request because it's not meant for them. They don't have MAC address B, IP address B. But when VTEP2 forwards it to both its connected end systems, this node is going to realize that the ARP request is actually meant for it. It is the owner of IP address B. So end system B will generate what? Like I discussed on the previous slide, it generates an ARP response. End system B generates an ARP reply and sends it towards end system A. Okay. So now VTEP2 will receive it. VTEP2 will look up its table. And this time, VTEP2 will find an entry which says that end system A is connected to VTEP1. So how will the ARP reply come back? It doesn't need to be flooded. It gets tunneled through the underlay network directly to VTEP1. Okay, so basically VTEP2 will encapsulate the ARP reply. Like we saw MAC in UDP encapsulation, it will put a VXLAN header, it will put a UDP header, encapsulate it in an outer IP packet and send it unicast it to VTEP1. How does the traffic come from VTEP2 to VTEP1 in the underlay network? Naturally gets routed via the clause network using the routing protocol. Whether OSPF or BGP, whatever you're using, this gets routed from VTEP2 to VTEP1. Jyoti, I haven't read your question. I'll just complete this and I'll read it and come back to your question. So VTEP1 receives the ARP reply. de-encapsulates and delivers it to end system A. Now, what does end system A know? End system A has gotten the MAC address. Okay? The MAC address information is learned, and now additional packets can be fed. Data traffic can now flow via end system A to end system B. By the way, at this time, VTEP 1 has also learned that end system B is reachable via VTEP 2. So the learning is also parallelly happening as the as part of the flood and learn control plane protocol. Okay, let me read what Jyoti has written and then come back. So in summary, I mean, before even I read that, in summary, it's like any other flood and learn layer 2 network. But rather than using broadcast, the only intelligence that we've applied here is because the underlay network is an IP network, we made use of multicast. We've created as many multicast groups as the number of VNIDs. Every VTEP joins a multicast group based on its association to a VNID. Right? And then the flooding happens via multicast rather than broadcast. That's how it works. Okay, Jyoti's question. VXLAN uses multicast group to flood unknown broadcast traffic across all VTEPs in the same VNI. So every switch sees the ARP broadcast request like a normal LAN. That's why flood and learn multicast based control plane. That's correct. Yeah. So think of every VXLAN segment, which is denoted by a VNI, as a layer 2 virtual network. And like on the previous slide, we said in a layer 2 network, every node gets an ARP broadcast message. Here also, every node gets the ARP request. But in the underlay network, it's multicast. Okay. So yes, Jyoti, what you said is right. Multicast is the method that we are using in the underlay IP network to simulate a broadcast in the overlay network. In reality, when you just consider the overlay network will still feel it's a broadcast. All these end systems are getting the ARP request as if they were part of a layer 2 broadcast domain. But in the IP network, it actually flowed via a multicast group. Okay, Yuvraj has put something up also. End system A, yeah, sends it to VTEP 1, that's correct. Which means end system A is the MAC address for node A. So in the ARP request always carries the IP address of B and the MAC and IP address of A. But in the ARP response, B's MAC B and IPB will both be carried. Okay, and the ARP response will be sent towards MAC A. It's a unicast layer 2 response towards MAC A. End system A and end system B are the terminology that we're using to denote the nodes. But MAC A is the MAC address of that node and IP A is the IP address of that node. Okay, so this is one way of implementing the control. Okay, Yuvraj says, I'm talking about the table which is displayed in the diagram at all VTech. Yes, in that table, end system A and end system B is the MAC address of those nodes, right? Because it's a layer 2 network segment that they are creating as an overlay network. They are recording the MAC addresses and the reachability via which port and which VTEP. See, if it was a layer 3 overlay network that I was creating, I would worry about IP addresses. If it's a layer 2 overlay network that I'm creating, MAC addresses is what I need to know. Because what I'll get from the end systems will be L2 frames. Okay? These L2 frames will have destination MAC addresses. So based on the destination MAC address, I need to know which VTEP to tunnel the packet towards. So here end system A, because we are assuming I'm creating a layer 2 overlay network, this is the MAC address. Okay, so this is one way of implementing the VXLAN control plane and exchanging reachability information, but it's obvious it can only work in small to medium sized data center network. Why? Because as the number of VNIs grow, as the data center network grows, the number of VNIs grows, the number of multicast groups will become huge. The multicast traffic will become very large. And just like with broadcast traffic, we treat it as an overhead. The multicast traffic is also overhead, and the percentage of overhead compared to the regular data plane traffic will start to grow. So the efficiency of the network, a lot of bandwidth of the underlay network will start getting utilized for carrying multicast traffic rather than real data plane traffic. And therefore, it's best suited for small to medium sized networks. What should I do in larger size network? Just like we do in the internet, we introduce a routing protocol. Okay? So the second approach or the second control plane protocol that VXLAN supports is called the multi-protocol BGP. It's also called it's also extended to call it a multi-protocol BGP for Ethernet VPN. Okay. Now, where does this terminology come in? As I said earlier, this is not a new protocol. Like IGMP was not a new protocol. This is also not a new protocol designed for cloud environments. No, it's a protocol that's existed for many decades. It's been used in the past for creating virtual private networks for enterprises which are connected over the internet. Okay, so the VPNs that we use when doing work from home is a special case of MPBGP EVPN. Okay, so in general, how has this protocol been used in the past? So you have a service provider, right, whose could be okay. Let me come to the service provider slightly later. Let's first talk about consumer. So let's say I have two enterprises. Let's call it organization X and organization Y. Now, organization X exists in Hyderabad, has an office in Hyderabad, has an office in Bangalore, has an office in Delhi NCR. Organization Y also has an office in Hyderabad and also has an office in Bangalore, and then it has a third office in Pune. Now, these organizations, because they have multi-location offices, they want to create a virtual private network. So by now, I don't think I need to define a virtual private network. We all understand what a virtual private network is. Like a private network, it's an overlay network, firstly, and that's why the term virtual. Virtual means it has to be an overlay network. PN private network means it should appear as if it's a private network, which means they are connected to each other. Okay, so let's say this is Hyderabad, this is Bangalore, this is NCR, and this is Pune locations. Now, the gray organization, which is actually organization X, it has its three individual networks in each three locations. Right? But what I want to do is I want these three locations, this one, and this one, to be connected together via tunnels to each other such that they can feel that they're part of the same private network. So the difference in location, Bangalore, Hyderabad, NCR, should not be a concern. Employees sitting at any of the offices should be able to work as if they are part of a global private network for organization X, right? And that's why we are calling it a VPN, a virtual private network. Now, because they're geographically segregated, they will have to use the services of an underlay network which spreads to all three locations. This underlay network could very well be the internet. Right? So I can, and that's normally what we do when we sit at home and connect to my enterprise network. I use the internet to connect. I create a tunnel to the internet, and we still call it a VPN, a virtual private network. But most often, enterprises don't use the internet in the raw form to create their private virtual VPNs across locations. They use a service provider, right? A service provider like Reliance or Airtel, who underneath use the internet, but on top provide certain value added services, including SLAs and quality of service. Okay. So many times these service providers over the underlay internet, okay, so they can use the internet, or sometimes larger service providers also create their own communication network. I'm not sure if you're familiar or not, but larger organizations like AWS, for example. When AWS, I think I may be mistaken, but AWS has about nearly 200 data centers across the globe. I mean, it's on the higher side, maybe somewhere between 150 to 200 data centers across the globe is what AWS has. To connect their data centers together, they've set up their own fiber optic network. So AWS data center connectivity, multi-site data center connectivity doesn't rely on the internet. They have their own optical network that they've set up to connect their data center. All I'm saying is internet is one way to connect multiple locations. But if you have a larger service provider, a service provider can set up its own communication network as well by laying cables and setting it up. So mostly organizations, when they have to set up such VPNs, they actually go to such a service provider who has presence in all locations and has his own communication network set up, which is not a public network like the internet, but it's a more reliable network. Right? Most of the time, these service providers set up a MPLS network. MPLS is a multi-protocol label switching network. Okay. So, in a sense, what I'm saying is there are two parties involved over here. One is generally the service provider. The service provider is who? He is a provider of communication services. He enables connectivity across locations. He has a communication network which he has set up by laying communication cables, setting up his own routers. So these edge routers are called provider edge. P stands for provider. He's a service provider. The service that he's providing is connectivity. So the edge routers are called provider edge, and the core routers are just called provider core routers. Right? So this is kind of the backbone of this service providers network. And this is the next level leaf nodes, and then they connect to the consumers. And therefore, this is called the customer edge, CE, customer edge. So these are all IP routers, nothing special. Or if this is the MPLS network, then these are actually all these PECEPs, they are called label switching routers. MPLS is an IP-like protocol. Okay, we've not talked about MPLS and I don't intend to. But MPLS is actually label switching. It's a kind of a circuit switched approach in a packet switch network like IP. Okay, that's what I'll just say for now. It's a more reliable way of communicating than the IP. IP is always considered a best effort network. And that is why we need TCP on top if reliability is needed. But IP networks are best effort.
We saw that if routers get full or queues get full, packets get dropped, no resource reservations happen, unlike in circuit switch networks. So MPLS borrows certain ideas from circuit switch networks, but some of the principles from IP networks, and it's a new route, it's a different networking protocol, MPLS. Okay. So many service providers have their own MPLS networks, which are label switching networks, um, which provide connectivity services. So the service they are offering is connectivity service. Okay. So having said this, what is it that these guys need? Because there are multiple consumers who may be taking service from the service provider. Every consumer wants that between their networks, tunnels should get set up over the service provider network so that they can have their own virtual private network set up. Okay? The white one will want its own tunnels, gray ones will want their own tunnels. Okay? So this has existed for decades. Right? I'm sure many of your organizations use something like this. If you are a multi-site organization with many branch offices and a head office, and your networks are connected, then you are most likely using the services of a service provider to connect your head offices with branch offices. These could be leased lines that you may have leased with fixed bandwidth, or they may not be leased lines, but so there are service providers like Tata Teleservices who provide these kind of services. Tata Teleservices, Reliance, I don't know what the Reliance service is called, what's the name, but Tata Teleservices, Reliance, they are all service providers who provide these kind of services. And mostly organizations take service from one of these service providers. They guarantee some SLAs, some bandwidth, and of course, security. These tunnels are secure tunnels that they create. Right. Now, that was the background. Now, how is it ensured that traffic between these VPNs can flow seamlessly? I need reachability information to be exchanged over the service provider network. By reachability, I mean, let's say this is network prefix A. So this is the subnet. Right? There are nodes that belong to, let's say, A.B.C.star. Nodes here belong to A.B.B.star, and nodes here belong to A.B.A.star. These are like three different subnets of the enterprise. So I need to exchange this reachability information saying this customer edge router is able to service all nodes in this prefix A.B.C.star. This customer edge is able to service all these prefixes. This customer edge is able to service all these prefixes. So one is, how does each customer edge exchange the prefixes that are reachable via it? That's one thing that I need to do. The second thing, which is also important, is that this exchange of reachability information needs to be restricted between only the CEs belonging to one organization. Okay? That is the way I want these reachability information to be exchanged. For all you know, these prefixes could all be private IP addresses. These may not even be public IP addresses. Okay. So I want a method for reachability information exchange where I can exchange prefixes between the customer edge routers over a service provider network such that a VPN can be created and routing of traffic between these CEs can happen as tunnels. And this is what can be done using BGP. So we saw earlier that BGP is a method that helps us, it's a path vector protocol that helps us exchange network prefixes. It also helps us tell which is the next node, next hop. So CE is the next hop. The prefix is this, the next hop is the CE. So I can exchange this reachability information. The only additional thing that I need to do is make sure that the reachability information is only being exchanged between CEs belonging to the same organization, not to CEs of other organizations. And this is where EVPN comes in. So MPBGP is an extension to BGP protocol. BGP only exchanged IP prefixes. Multi-protocol BGP came in as an extension to BGP in order to help exchange any kind of prefixes, not just IP, but any other protocol as well. And hence the name multi-protocol BGP. Okay? So if your BGP protocol can exchange IP prefixes, I can have an extension to that BGP protocol that uses the same ideology, but allows you to exchange any other protocol prefixes as well. And that is what MPBGP is. EVPN is the part which makes sure that the reachability information exchange is only done between edge devices that belong to the same organization. So that's where the Ethernet VPN part comes in. So MPBGP EVPN is an existing protocol which already exists in the internet. It is used for these purposes to connect organizational networks to each other. By the way, if you want to take an example within BITS Pilani, all our labs, let's say this are remote labs, not the virtual labs, but the remote labs. They are all located in our Hyderabad campus. And you are sitting all over the country. The service provider, in our case, we take services from Tata Teleservices to enable our remote labs to be accessible to all of you via the internet. So you use the internet to connect to the Tata Teleservices network, and via that there's guaranteed SLAs that are committed for your traffic to reach our remote labs and thereby do the lab exercises that are required. Okay? So this has been the way to create enterprise specific virtual private networks over the internet, over service provider network for many decades. These protocols have existed for a long time. Now, what do I have now in the cloud environment? If I try to map the cloud environment to what we just discussed, there is a one-to-one mapping that I can do. I can say the service provider core is nothing but the underlay data center network. I can say that these individual networks are nothing but tenant-specific subnets. Tenant subnet A, tenant subnet B. Okay? And the service that I need is to be able to connect these together. So the CE can be seen as a VTEP. The traffic generated from within this subnet comes to the VTEP. The VTEP can tunnel it, send it to the other VTEP, and that way the traffic can reach the VM within the tenant subnet B. So there's a one-to-one mapping between what we need and what already exists on the internet to support enterprise VPN services. And the same protocol that we use on the internet, MPBGP EVPN, is what we've adapted. We've not even adapted. It's something that we've picked up and reused with VXLAN to make the second control plane that we have for VXLAN. So let's now, with that background, let's now go through these slides. What is the VXLAN MPBGP EVPN control plane? As we said, the flood and learn method creates significant flooding traffic. Therefore, you cannot expand the network to a larger size network. And the solution to this problem is to have a EVPN based MPBGP protocol introduced on the VXLAN control plane. This is a short for Ethernet VPN or Ethernet Virtual Private Network. I use the same methods as what are used in the BGP MPLS protocols used on the internet by creating the PE node as the VTEP. Sorry, I mentioned wrongly. It's not the CE, the PE, which is part of the data center network. That's the VTEP. And the CE actually can be seen as the sender, the V switch, which is sending the traffic. PE is the VTEP. I can treat the VE as the VTEP. And these VTEPs use the MPBGP protocol to advertise reachability. The prefixes get exchanged using the MPBGP protocol. So a normal routing protocol like BGP is what I can use to exchange prefixes. See, the problem is very simple. I have VTEPs, and these VTEPs service a set of VMs, and they need to exchange this information amongst themselves. I can use over an IP network routing protocol like BGP to do that. But because I also want the tenant specific information to be isolated from one tenant to the other, I use the eVPN extension to MPBGP to do that, just like I did on the internet for providing enterprise service. Okay, so I don't think we need to go deeper into it to understand, because then we will have to get very deep into individual protocols, MPBGP, eVPN, which I don't want to do. But I'm just saying that this is an existing protocol. Okay, so this is one slide on MPBGP, which I already mentioned. Traditional BGP4, the information that it exchanges is IP information. But the field that it has a field called NLRI, Network Layer Reachability Information. So when BGP4 was designed, it was designed only to manage IPv4 prefix exchange amongst border gateway routers. But MPBGP was implemented as an extension to basic BGP, because the world started moving beyond IPv4 to even IPv6, and I can have even other network layer protocols as well. So as IPv6 came in, BGP4, which was designed for IPv4, could not be used. So an extension to BGP was designed, which was called multi-protocol extensions for BGP or MPBGP. MPBGP extends the network layer reachability field of BGP4, generalizes it so that you can use it for other network layer families as well. Okay? So MPBGP is what we use today in IPv6 networks. I can use it for other network layer protocols as well. It's a generalized extension to the basic BGP protocol. Okay. Yeah, these are slides I want to skip. Okay, I'll just skip them. It gets deeper into BGP, eVPN. There are different types of routes that you can carry. Because it's a generalized extension to BGP, there are different types of route types that are explained, route type 4, route type 3, and so on. Let's skip this. I don't think we are going to get so deep into our discussion. We can avoid that. So rather than that, because we just have 8 more minutes left, I want to spend some time just to now complete the entire discussion that we've had so far by summarizing our single site data center network and looking at all varieties of data plane and pathways that exist, and summarize for completeness. So we've covered VXLAN control plane. I just want to spend last 7-8 minutes talking about a little bit about the VXLAN data plane and all the different paths that can exist. Okay. So what we've learned so far based on the VXLAN control plane is that there are ways that exist in the VXLAN protocol specification that enable VTEPs to learn of how to transfer or tunnel the overlay network traffic between themselves in order to cater to overlay network traffic forwarding requirements. What kind of data plane traffic exists in the overlay networks? Okay. So there is different type of traffic that can exist. Okay? And as we said earlier, the traffic in a data center network, we can classify it as east-west traffic if it is getting transmitted within the data center, or north-south traffic, which can be going out of the data center. So traffic that is transmitted within the same subnet of an overlay network. Okay. Now, I'm going to use in this slide the term VPC to denote a tenant specific overlay network. This is the term which AWS uses, right? A virtual private cloud network. It's a overlay network that's been created for a tenant. So I can have traffic within a overlay network or a VPC that belongs to the same tenant being forwarded between one VM to the other VM, where we are saying both VM are part of the same tenant. How does this traffic flow? Okay, where is it? Yeah, so this first one. Yeah? The gray dotted arrow is the traffic within the same subnet of an overlay network. Right? How does this flow? So this is the Tor switch we've learned acts as the VTEC. It'll be forwarded by the Tor switch after layer 2 VXLAN encapsulation. So the VXLAN encapsulation will be done, forwarded from the source Tor switch to the destination Tor switch, where it will be decapsulated and forwarded to the VM. So this is how the traffic flows. This is the NVE. The traffic flows and gets tunneled. And this is your east-west traffic. It's within the same data center. Right? Within the same subnet. So the subnet is the same as you can see 192.168.1.10 okay, /24, which means you only cater to the first three 192.168.1, 192.168.1/24. It's the same subnet. Okay? So in the same subnet, I just tunnel the traffic using VXLAN encapsulation. I can use VXLAN to even transmit traffic between subnets of a VPC. So like on the previous slide, I said, this could be one subnet of your tenant. This could be another subnet. The overlay network, the virtual network that I'm creating could internally have multiple subnets. Traffic can be transmitted between subnets of a tenant overlay network. Right? But what did we learn when we talked about network fundamentals? One subnet is treated like a L2 switched domain. Okay. So I used layer 2 VLAN encapsulation, which was the MAC in UDP that we've been talking so far. I take a L2 frame, encapsulate it into UDP, and then send it over the layer 3 network of the data center. But when I have to send traffic across subnets, we know that between subnets, we always use IP routing. Okay. So what is the traffic that will be generated by one subnet? It will be a layer 3 IP packet. So I will use layer 3 VXLAN encapsulation. It's basically taking IP packet of one subnet and encapsulating into UDP. So remember I said we are saying back in UDP, but in reality, I can even do IP in UDP encapsulation. Because the inner packet, I don't care. It could be a layer 2 frame. It could be a layer 3 packet. So when traffic, the overlay network that I'm creating for a tenant could be one subnet, but it could also be two different subnets or three different subnets. And when I have to send traffic from one subnet to another subnet, across subnets, I always send IP packets. This we've learned in our IP network fundamentals. So one VM will generate an IP packet for a destination VM, which is in another subnet of the same VPC, the same overlay network. VXLAN can support layer 3 tunneling also. We've learned this. So VXLAN tunneling can be used to transmit traffic across subnets as well. So where is that example? Yeah, this one. Dark black. So this is 192.168.1. This is 192.168.2. There are two different subnets. I can still use, this is L3 encapsulation, L3 in VXLAN encapsulation. And that is the other type of traffic that you will see in a modern data center within the overlay network of a tenant, but across subnets. Okay? There are the VMs belong to two different subnets. VXLAN still supports that. Then there's the third type of traffic which is transmitted between VPCs. Okay? So between VPCs definitely means it's across subnets. Okay, so this is kind of like one tenant sending traffic to another tenant. The client machine being a VM in one tenant's network, the server machine being the tenant in another tenant's network. Think of it like that. So it's traffic across subnets, so it has to be L3 encapsulation. But generally, between tenants or between VPCs, I will have some security requirements. I will say that this traffic, before it enters tenant 2's network, I want it to pass via a firewall. I want it to go through an intrusion detection and prevention device. So the tenants will have some kind of security needs. So such traffic, when it's going between VPCs, this is the dark gray, this gets tunneled via where I can't make, yeah, it's going here, via value added service devices. Remember, I talked about some special value added service devices, service by leaf, service leaf. This is how the traffic will go between tenants. So it's layer 3 encapsulation, IP in UDP encapsulation. Right? So I take a IP packet, put a VXLAN header, then an outer IP packet, and then send it through the data center network, underlay network. But I also force route it. I create a service chain that goes via some service switches, VAS switches, like a firewall. Okay? This is how traffic can flow between VPCs. Again, using VXLAN encapsulation. Finally, there is that north-south traffic, which we always understand. NS, traffic coming from outside the data center. That was the first thing we started with, that there is some traffic that comes from outside, which is this dotted black. So this comes from the internet via the egress router, goes to the spine border leaf. Border leaf will pass it through a firewall, load balancer before routing it towards the server. So again, this is also your L3 encapsulation, because the outer packets that are coming from the internet, they are IP packets. Right? So there are 4 different types of traffic that you will observe. 3 types which we said are east-west, and one which is the north-south traffic, which is flowing in the data center, in a modern data center. And VXLAN being the general protocol that it is, it caters to all these type of traffics. Within one VPC, within a subnet, within a VPC, across subnets, across VPCs, and for a VPC coming from the internet. VXLAN is a common protocol that is able to support all types of traffic within a modern data center. Okay, so this is what I wanted to cover with respect to VXLAN, and actually this completes our discussion on single site data center networks, all topics covered. Next class, I will start with the topic on multi-site data centers. Okay, so I'll first introduce why do I need multi-site data centers, what kind of use cases exist, and how does networking work in a multi-site DCN. Okay. Once we discuss that, I'll take a specific example of a multi-site data center network and explain how that works. Okay, Yuvraj has a question. How about the data flowing from host to internet? Exactly same before. Yeah. You see both these diagrams. Sorry, I removed that. They are bidirectional arrows each way. So coming in, going out, they are bidirectional arrows. So it flows the same path. Of course, you might say that going out, I don't need it to pass through a firewall, but many times I do, because even egress traffic that is flowing out, tenants do want to observe, put in policy rules even on egress traffic. It's not just on ingress traffic. So it takes the same pathway out as well. Okay. Okay, so thank you very much, guys, for joining in. And see you again next Sunday when we start with a brand new topic on multi-site data center networks. Thank you for joining. Bye bye. Have a good rest of the weekend.